Hello again, this is Gallagher Fluid Seals. Today, we continue our series on the world's most popular perfluoroelastomer, Kalrez. The agenda for part 2 of our video series on FFKM will compare conventional elastomers versus Kalrez. We will take a deep dive into what makes Kalrez so special for a wide variety of industries and applications worldwide. Conventional elastomers come in many different types and grades. For instance, there are approximately 60 different grades of Viton, a fluoroelastomer, and 18 grades of Nordel, an EPDM. To further complicate this situation, each O-ring manufacturer or rubber fabricator then has a number of specific custom formulations or compounds for each grade. This multiplier effect essentially creates hundreds of different compounds in these conventional commercial elastomers. Since Kalrez parts are predominantly used in sealing systems, it is useful to review the basic properties of the most popular seal materials. Other elastomers used for sealing include epichlorohydrone, ECO, PNF, polyacrylates, polysulfides, butyl, and neoprene. These materials are generally used in less demanding applications and have not been included for review in reference to use in seals. Many grades are available of each base polymer that can be compounded to fit specific performance requirements of hardness, modulus, tensile strength, and elongation. However, regardless of what the compounder does, the basic chemical resistance properties of the polymer chain remain the same. We can, therefore, classify the properties and upper surface temperatures of each polymer with some certainty. Nitrile, manufactured from acrylonitrile butadiene copolymers, referred to as NBR or Buna-N after the original Bayer trademark, is the workhorse of the sealing industry. Acrylonitrile butadiene copolymers are relatively low-cost elastomers. The acrylonitrile content, which can vary from 18 to 48%, influences the oil resistance. The higher the content, the better the aromatic oil resistance. Carboxylated types offer higher service temperature limits, up to 250 degrees Fahrenheit. Peroxide and sulfur-based cross-linked systems are also used for certain applications. Ethylene propylene copolymers, or EPR, are peroxide cross-linked. DuPont's EPDM, Nordel, which as a terpolymer has diene added to the chain, which has the ability to be cross-linked with peroxide or sulfur-cured systems. Ethylene propylene elastomers are relatively inexpensive, and the best in pure uncontaminated steam-water service, up to 320 degrees Fahrenheit. This elastomer is often used in boiler feed water applications and for heat exchanger gaskets. EPR rubber, however, has no oil resistance and very limited chemical media resistance. These elastomers have been proposed for use up to 450 degrees Fahrenheit in the absence of oxygen, as in downhole geothermal well service. Silicone was one of the first elastomers used for high-temperature service and is the highest production specialty elastomer produced today. Silicones have limited original physical properties at room temperature, but they retain most of their original tensile strength and tear resistance at elevated temperatures. Silicone is commonly used over its temperature limit, possibly because degradation byproducts are not nearly as toxic or corrosive as those produced by fluoroelastomers. Rapid hardening and embrittlement can be expected over 400 degrees Fahrenheit. Silicone rubbers have no aromatic or aliphatic oil resistance, and in general, poor chemical resistance. Conversely, silicones have the best low temperature rating of any elastomer, down to negative 112 degrees Fahrenheit. It is important to note that at high temperatures in the absence of oxygen, silicone will begin to revert back to its original monomer state, resulting in a cheesy consistency and complete loss of physical properties. Fluorosilicone is a good example of protecting the basic elastomer chain through polar bonding. The addition of fluorine to the basic silicone chain imparts very good oil-fuel resistance to the elastomer while retaining excellent low-temperature properties. Otherwise, fluorosilicones are much the same as silicones, apart from cost, which is much higher. There are many grades or types of fluoroelastomers utilizing various cross-linking systems to achieve specific properties. The higher their fluorine content by weight, the more resistant the fluoroelastomers are to chemical media. Accordingly, TFE, propylene, or AFLAS will swell much more than the Viton A, B, or G types in most chemical media. There are many grades of Viton in the A, B, and G types, which may be compounded to fulfill specific functions, like anti-extrusion or lower compression set. Different cross-linked systems have a pronounced effect on water resistance. For instance, the peroxide lead oxide cross-linked Viton GF types are superior to other Viton types in hot water and steam. There is a low-temperature service Viton, GLT, which has chemical resistance similar to Viton A. Viton B types have a high-temperature heat resistance up to 425 degrees Fahrenheit. All other grades are rated up to 400 degrees Fahrenheit. On the other hand, all fluoroelastomers will quickly swell beyond usefulness in ketones, esters, and some ethers. Since Kalrez has the highest fluorine content of any commercial elastomer, approximately 73%, and is fully fluorinated on the backbone of the main chain, it is unique in offering an unsurpassed combination of heat and chemical resistance. Comparing the chemical structures of fluoroelastomers to that of Kalrez clarifies why Kalrez parts have such an outstanding performance in terms of heat and chemical resistance. Fluoroelastomers, Viton and Aflas, have various non-fluorinated sites in the polymer backbone, leaving them vulnerable to chemical attack. It is at these carbon-hydrogen sites unprotected by the polar umbrella of fluorine that the destruction of the chain can be initiated by aggressive environments or with temperatures. Furthermore, the cross-linking systems used with fluoroelastomers is phenol, or peroxide, making it susceptible to attack and unable to survive temperatures over 400 degrees Fahrenheit. By comparison, Kalrez structure is completely protected by fluorine on every carbon or oxygen atom along the entire length of the polymer chain, and in most cases the cross-link is also fluorinated, further stabilizing the whole structure. All the cross-link structures used in Kalrez are designed to be stable up to 600 degrees Fahrenheit. Kalrez parts are often used in environments where conventional elastomers, such as nitrile, EPR, fluoroelastomers, or silicones, are satisfactory from a chemical resistance point of view, but the actual service temperature of the application exceeds the higher temperature rating of the elastomer. In addition, in aggressive chemical environments, Kalrez may be required well below the upper service temperature limits of conventional elastomers. Nitrile, EPR, fluoroelastomer, and silicone will become hard and brittle when used beyond their upper service temperatures. Another definitive advantage of using Kalrez parts is that they will not and cannot, due to their unique chemical structure, harden or embrittle like other elastomers. Conversely, Kalrez actually becomes slightly softer and retains its sealing ability when in service at elevated temperatures. These are the maximum service temperatures of most common elastomers. Kalrez is by far the most heat-resistant commercial elastomer. The ASTM D2000 test standard determined at what temperature over a given time the elastomers retain this specific percentage of their original properties. Judging from the results, Kalrez is by far the most heat-resistant commercial elastomer available today. The bar chart here represents the swell of various seal elastomers in an aromatic media. What you see is gasoline at moderate temperatures of 130 degrees Fahrenheit. Silicone clearly illustrates the large swell of an unprotected molecular chain. As the degree of fluorination increases, fluoroelastomers begin to exhibit better swell resistance. Elastomers, which swell over 15 to 20% in a chemical media, are not suitable for most O-ring applications because standard grooves do not have enough free volume to accommodate the swollen ring. Kalrez, which is fully fluorinated, hardly swells at all in this example of aromatic fuel or almost any chemical media. Kalrez, when compared to other conventional elastomers, exhibits far superior performance in both heat and oil resistance. Kalrez is unique not only for its heat and chemical resistance, but also for its ability to maintain its properties over an extended period of time in the worst conditions. This is what sets Kalrez apart from other conventional elastomers. Thanks for watching our video today about Kalrez FFKM. Stay tuned for our next video where we will discuss Kalrez compression set resistance, sealing force retention, and more.